Hello YouTube, RJ. Hey, we just finished up a series of tech talks involving capacitive reactance. And so I was thinking, what am I going to do next for the next tech talks? And I thought, why don't we do a introduction to digital electronics? We've already talked about a lot of analog stuff on the channel, and I thought, why don't we kind of wade in the shallow end on digital electronics? I'm sure there's some of my viewers out there that would like to learn about digital electronics in a way that's friendly and easy and not throwing you off in the deep end of the pool. So I thought about it and I thought, how would I do this? And what I thought was, how about I start out with the intent of doing 2 videos? It could be 3 depending on how long the material runs, where we ease in like we did with the capacitors and we talk about digital electronics. The way I wanted to approach it was I said, let me pick a device, a simple device that we could use and work into developing a little circuit with that would be easy to use. And along the way, I could teach you a lot about digital electronics. The first device that came to mind was one of my favorites. It's an oldie, but a goldie, is the 74HC595 chip. It's an 8-bit shift register. A lot of these were used in a lot of different systems, and I thought, why don't we end with having a circuit that functions using the 595? Actually, we're going to use a couple of them in it. We could run it with Arduino. We won't get so much into the actual Arduino Nano that we're going to be using to send the data to this. We're going to start out by first talking about what is digital electronics. What is zeros and ones? Now that may seem uber simple, except it's really not. There's so much in that. A 0 is not always a 0 and a 1 is not always a 1. And I want to go through all that. So here's how I thought we'd approach this. Start out by talking a little about 0 and 1s and what digital electronics is. Then progress over and pull up the data sheet for the 74HC595 chip, walk through and show the critical stuff on the data sheet, what it really means, how it applies to you, and why you should be able to look at the data sheet and pick these things out. Then from there, we go over and create a schematic for a little circuit using the 595 chip. And then that's probably where I would end the first video. And then we would finish up by building the circuit on a proto board and then writing a little bit of code just to drive it so that you could see how it works. I can hook the scope up and let you actually see the digital signals. And in there, leaving you with a basic understanding of how digital circuits work, a little bit of information on how to design them, give you a stepping stone to start with if you become interested in digital electronics. I'm going to get some stuff together and we'll start on this first video. Okay, let's talk about the very first thing we have to get into. What is digital? And digital is when you refer to everything with 2 states, on or off, 0 or 1. Typically in digital, we talk about 0 and 1 because we work in binary numbers. Since digital is either 2 states, there's actually 3 we're going to talk about. We have to talk about what is a 1 and what is a 0. And you have to have a reference. It's sort of like trying to measure voltage. If you don't know, if you put your positive probe on something, but you don't have anywhere to put your negative probe, you don't have a reference. You can't really measure. You don't know what's high, you don't know what's low because you don't know what the reference for that is. And in digital world, that's very important. So when we talk about a 0 or 1, it's not the same for every component. It's not the same for every circuit. Let's look at what digital signals are. We call them zeros and ones or highs and lows. This is what people believe. This is the basic perfect world contention. And that is that you have a signal, and in this case we're going to say that the device that we're working with works at 5 volts as our supply voltage. The assumption is that when the signal is 0 volts or ground, if you want, we'll come back to that, but when it's 0 volts, you're not supplying current to it, it's a 0. But when the signal is at 5 volts and you are supplying current to it, then it is a high. So then it is a 1. So 0 when we're at 0 volts and a 1 when we're at 5 volts. And as time goes by, these signals go on and off and on and off. And this is a very simple way of looking at it. But in reality, that's not how it works. If we look at the second set here, the only difference you're going to notice is there are 2 green bars. And what I'm trying to signify to you here is that 0 is a range of voltages. It's not 0 volts. It's 0 to some volt. And the old TTL logic, it could be anywhere from about a diode drop to about 2 diode drops. So some stuff was 0.8 volts, some stuff was like 1.6 volts. Between 0 and somewhere in here on the older chips, different chips are different, things would be considered to be 0. So you have a range of 0. On the other end, a high or 1 is also a range. Typically, rough rule of thumb is about 80% of your supply voltage. This means that you've got some range of places where you're 0 and 1. But notice that in here, it appears that you're neither. So that doesn't make a lot of sense. If I'm down here and I'm 0 and I start moving up, what do you mean that I'm nothing here? Well, that's not true. You're not nothing. You just don't change in that range. If I'm 0 and I start going up, I'm going up here, and I'm in this range, I'm still 0. If I was 0 before, I'm still 0. But once I break this line right here at the bottom of my range for high, I'm going to change states to high. Now, if I was to dip back down in this area, I got up and became high, and then I dipped down below this, I would stay high until I got down to the top of the low level, in which case I'd change states. Now, why is that? Well, this is called hysteresis, and I probably pronounced that poorly. As y'all all know, I speak one language, English, and I don't do that exactly great. This hysteresis in here is very, very important in digital circuits, and that's because when you switch to a 1 in a digital device, what you're really doing is you're turning on logic gates, you're turning on transistors. And as we all know, when you turn on a transistor, you're likely probably going to flow some current. There's going to be something typically hooked to it that's going to pull current. So in a digital circuit, what will happen to you is this is high, this is low. You're low. You decide to go high. So let's say that it's the way that most people that don't work with digital electronic believes it works. We're going to do 2 bars here. We're going to call this 0 and it's 1 here. You're 0 and the voltage, you say, okay, I'm switching to 1. You turn the power on and it starts rising. Well, it doesn't instantly go up. As you know, there's always a little inductance and capacitance and everything. It doesn't go straight up. It slopes upwards. At some point, it will break this threshold and switch to become a 1 right here. When it does, transistors are going to come on. When transistors come on and current starts flowing, sometimes your voltage sags a little. So it's very easy to break into 1 and then immediately drop below that threshold momentarily as things charge and then come back on in. The problem we have with digital circuits is if this happens, if it worked this way, you would have a 1 and immediately switch to a 0 and then immediately switch back to a 1. You have corrupted data now because you only really changed to a 1. So that would corrupt all of our data if it worked this way. So now go back to this and imagine that we say, no, you don't go all the way up here. You stop here as 0 and you start here as 1. And in here, you don't change. That you don't change in the middle is called hysteresis. And what it means is once you switch states, you've got a ways to go before you'll change state again. Now let's take our scenario. Let's start from 0 and we're going up to become a 1, but we have to go all the way up to this line at about 80% of our supply voltage. And we get here and we get stuff turned on that sags the voltage. It drops down in this range and then it goes back up. It works perfectly. And here's why. When it switched to 1 right here and then sagged in here, in this area, we don't change. So it stays a 1. When it climbs back up and goes over the threshold of being a 1 again, it's already a 1. So it's not going to do anything. So you get looks like a clean transition from 0 here to 1 here. Over here, with this setup, we would have got a 0 here, a 1, a 0, and a 1. And we would have corrupted data. We're going to see this in the data sheet. I'm going to show you where it actually tells us where these points are, where the thresholds for 0s and 1s are. These values can be different for different chips. They're definitely different for different voltages. If you've got digital chips, some of them are 5 volts, some of them are 3.3 volts, the logic highs and lows are obviously different for those 2 chips dramatically. This is the basics of what 0s and 1s are. I want to pull up the block diagram of the chip, the 595 chip we're going to look at, and walk through what the chip is and what it does. this is right out of the data sheet. It's just a little diagram. We're going to look at that and get that settled first, and then we're going to jump in the data sheet and look at some of these numbers and what you're looking for and what information you need to work with this. So let me grab that sheet. Okay, so this is a functional block diagram of a 74HC595 chip. Think of this section here as the chip. This is the lines going into the chip. This is the data we're going to provide. We're going to provide this data up here from our little microcontroller to control this chip. What this chip is it's 2 columns of registers, and there's 8 rows of those. This simplifies that this is repeated multiple times in here. And what happens is this line right here, SER, serial, I would say think of it, to simplify it, as data. I never like that they call it serial. Many logic chips will call that the data line. This is your data line. Then you have an SR clock. That is your shift register clock line. What does that mean? Well, this column here is your shift register. These are shift registers. This is storage registers, which they like to call registers. They just call these registers. These are actually, they use the language back and forth. These are the storage registers. These are the shift registers. But they call them the registers here. They call these the shift registers. So you have a shift register clock line. You have a shift register clear line. And what that does is whatever data is in the shift register, it clears it, all of them, in one shot. The little line over this means that to do this, you pull it low. If you pull this line low, all of these shift registers clear. They go 0, no matter what's in them. You then have the register clock, which is the clock to clock data through into your storage registers. Then you have one more line up here called OE. Again, notice the line above means to do what it's supposed to do, you pull it low. And that is your output enable. That turns on these outputs. If you pull this low, these outputs, they do their thing. If you pull it high, it turns them off. So now how does this all work together? Well, it's fairly simple. What happens is you have to understand you put the data in for the very bottom register, register 8 on this chip. You put that data in first. Keep that in mind. The most significant byte bit goes in first. We go all the way down to number 8, which is 7. It's 0 through 7. It's actually, they call it letters. So you go all the way down to H. You've got A through H. That's your registers. What you do is whatever you want in, if you're working with this single chip, whatever you want into H, this one, the very last one, you put it here. If you want a 1, you put your high, you turn your voltage on, you put your high up, and then in your shift register clock, you cycle high to low. You go up and then down, 1 clock cycle. When you do that, this data gets put in here. Let's say it's a 1. Now, when you're ready to put additional data, say you set 0 here now on the data line, you cycle your shift register clock again, and 0 will move into this register and push this 1 to this one. That's why they call them shift registers. You keep shifting it down. And you continue to do this to load up all of your registers that you want loaded. So in this case, we would clock 8 times on this line while setting the data here to the bits we want. And it would fill these registers. When we're done, we then cycle the storage register clock once, take it high, take it low. One cycle of this will shift whatever in the shift register assigned to it. In this case, here's A, here's B. B would take 1 from here and put it here. At the same time, when you did this same cycle, you only do this once, not for every one of them. This one's 0, it would put a 0 here. Typically while you're doing this, you have your output enable high. So these are not on because you don't know what state they're in. You're loading your data. Once you're done, then you pull your output enable low, and what's in here will show up here. You'll get 0 out of here, you'll get a 1 out of here, and it'll just stay there because this is a storage register. Now, we can now change what's in there by simply clocking in 8 more bits the same way we just did to fill these with new numbers. Maybe this one's going to be 1 this time, and this one's going to be 0, and this one's going to be a 1. So we clock that data in. We cycle our registered clock again, and now it would load 1 in here, 0 in here. If you haven't pulled the OE line, pulled it high to disable these before you do it, when you shift these will instantly change. Sometimes you want to disable it and then shift it in and enable it. It depends on your system. So with that, this is how it works. Okay, where would you use this? Why would you have this? Well, here's why. Let's say that you have a microcontroller and you've got, say, 6 pins available to use for your project, but you want to control 24 LEDs, or let's say 16 LEDs. Well, you don't have 16 digital out to turn on and off LEDs with. So what do? That's where these can come in. If you give me 5 lines on your microcontroller, and actually, if you don't want to do the shift clear, it's 4. If you give me 4 lines on your microcontroller, I can give you 8 with one chip. I can daisy chain another chip and do 16. I can daisy chain another chip, do 24, and literally on and on. The real only limit you run into is how quickly these things need to update. If you put thousands of these in a daisy chain, it would take you a long time to load them all. So if you need to change pretty quickly, that might become a problem. But when you're talking, well, typical 64 or 128, you can shift this in so fast that's typically not a problem. So that allows you to multiply the pins on your chip to handle a lot of LEDs. How do we add additional chips? Well, that's this pin right here. Here is your QH output. This QH is a little special. It's not your regular QH. It allows you to take this, come out, and go to the next chip and hook it to the serial, or I call it data line, on the next chip. Here's the next chip. We find the SER line and we connect it here. As we shift data through, when data gets to here and you shift again, this data will move over into the first slot on this chip. So you can now, instead of shifting 8 bits in, you shift 16 bits in. So you can control 16 bits. And all the other lines, this line you won't bring over to this chip. It gets it here. But the other lines, you just come off of these and run down parallel to these other chips. So however many chips you put on, you hook these lines the same way to each one of them, and then the first chip serial line gets the data from the microcontroller, and then each chip's QH out goes to the serial of the next chip. So the data just flows right down through however many chips you put in line there. So you can put in serial a lot. Like I said, a few caveats. There's a couple caveats actually. It's how long it takes to load, and you can get so many chips that your microcontroller has a hard time driving the lines. But then you put a buffer chip on there, and you can solve that very easily. With that, that's what this chip does, and that's going to be the end of this video. We'll pick up in the next one where we actually build it, test it, hook it to the scope, look at the data, see that we see this going on.